Hello and good afternoon, everyone. I welcome you all to my today's session where I will be talking about how to solve differential equations in Mathematica. As you remember, last week I talked about how to solve equations and then I shared with you how to calculate derivatives in Wolfram language. Today, we are going to take it a step further and we are going to see how you can use Wolfram language to solve differential equations. So in Wolfram language, there are two main functions. One is called Dsolve, which is normally used to find symbolic solutions to your equations. On the other hand, the Wolfram language function ndSolve is a general numerical differential equation solve. The objective of today's session will be more focused on how to use dsolve, what type of differential equations can be solved using this function. So all of my demonstrations today will be dealing towards symbolic solutions. So let's see what types of equations dsolve can handle. We can solve ordinary differential equations, also known as ODEs, in which there is a single independent variable and one or more dependent variables. Dsolve is equipped with a wide variety of techniques for solving single ODEs as well as system of ODEs. You can also use dsolve function to solve partial differential equations. Also, we'll be referring it as PDEs, in which there are two or more independent variables and we have one dependent variable. Finding exact symbolic solutions of PDEs is a difficult problem, but dsolve can solve most first order PDEs and a limited number of second order PDEs, which you find in standard reference books, can be solved using dsolve. Then differential algebraic equations, also commonly known as DAEs, in which some members of the system are differential equations and the other are purely algebraic, means they do not have any derivatives in them. As with PDEs, it is also difficult to find exact solution to DAEs, but dsolve can solve many examples of such systems that occur in application. Similarly, you can use dsolve to solve delay differential equations as well as solving integral equations, integral differential equations, and hybrid differential equations. So in today's session, we'll be mostly focused on solving ODEs and PDEs. So let's start and see what syntax is normally used. So function dsolve returns results as a list of rules. So this makes it possible to return multiple solutions to an equation. Similarly, for a system of equations, possibly multiple solution sets are grouped together. You can use the rules to substitute the solutions in other calculations. So this is the syntax of dsolve. We have a function, square brackets, we give the equation, we give the function y of x and the variable with which we need to differentiate. Let's take some examples and start learning the syntax first. So we'll start with the first order differential equations. So normally this is how you will find a differential equation written in a textbook. Now how you can translate this in Wolfram language to solve an equation. So we know we have a function called Dsolve, square brackets. So dy by dx is always written as y dash of x. So this translates into y dash of x is equal to sign. You know that in Wolfram language, you put double equal sign to represent is equal to sign. Then 2x plus 5, similarly, 2x plus 5 as it is. So this is function Dsolve. The equation is mentioned here. The second part is y of x. You always write y in terms of the variable. So y with x and then the variable x. So this is how you have successfully now translated a differential equation in the Dsolve syntax. And then you press Shift Enter and you will get the result for that. And you see there is an arbitrary constant value also coming. Let's take another example. So for example, you have to solve this type of equation, like a variable separable type. How you can do that? So we know Dsolve is the function, square brackets. This translates into y dash of x. For is equal, we put double equal sign. So it's 2y plus 5. So it's, we'll say like 2. Y is always in the form of y of x plus 5 and below x plus 2. And then the second other parameter will be y of x and the third will be the variable x. So now you have successfully translated the differential equation, which is first order differential equation, into proper syntax format. And then you can press Shift Enter and you can get the result of that. Let's take another example. Suppose you have this function and you need to write a Dsolve over that. So we type Dsolve. As you know, this translates into y dash of x because this is first order. So y function of x is equal to y dash x, double equal sign. Then we have, sorry, this should be here. And then we can say 2x plus y. Y is always written as y of x, and then down y of x minus x. Then you give the other parameter, which is in this scenario is y as a function of x and the variable x. And then you press Shift Enter and you can solve the equation. So this is a very easy way to translate a commonly mentioned differential equation into Wolfram language, and then you can solve it. So these are a typical example for solving first order differential equations. Now, how to do the syntax for second order differential equations? So similarly, in the same way, this is the second order differential equation. How you can do that? It's Dsolve function, square brackets for the function arguments. This is d square. So in this case, we have y double dash. So if this was d cube, we would have put like 3, but this is d square, so we put 2 times y double dash of x plus 2, this is dy by dx, that is y dash of x minus 8y, y of x. Similarly, and then double is equal to sign, this is equal to 0. So this equation has now been translated in this format to correct Wolfram language syntax. Now, the other parameters we need to mention is it's with respect to y of x. So this is y with respect to x and the variable x. And then you can press shift enter and you can execute it. And you see now in this scenario, because it is a second order differential equation, we have two constants. And Wolfram language has taken it as C1 and C2. So there are two arbitrary constants over here. Let's take another example. This is the same equation, but here now I have 6 cos of x as the answer. So the initial portion is the same. So I'll just copy Control Command L, basically takes the above input back, but now instead of 0 it is 6 cos of x. So I will change this, instead of 0 to 6 function cos with respect to x. The rest remains same. And then I can execute by pressing shift enter. And you see this portion is approximately the same because the arguments are the same, but due to this feature I have a different parameter value over here. So this is the easiest way I could explain how you can write and learn about the syntax. So we learned about how to use first order differential equation as well as second order differential equation. If there are more, you can just change the dash over here. Now let's take an example of how to take care about boundary conditions or initial value problems. So for example, this is your equation, dy by dx is equal to ky minus t, where capital T, t1 and k are constant, and the initial value for y of 0 is equal to t1, and t1 and k are all constant. So similarly, first let's translate this into Wolfram language. So function name Dsolve. So dy by dx is translated as y dash of x double is equal to, then there's a constant k bracket y always written as y of x because it is dy by x, so it's y by x minus capital T, it is a constant, bracket close. And then you need to give the other parameters like y of x and the variable x. Now how you are going to take care of the boundary condition? So basically this has to come here as a list. So what I can do here, you can get this into curly braces. You know that in Wolfram language, curly braces is used for list and ranges, and then you can mention over here. So here y of 0 is equal to, is equal to is double equal to sign and t1 as a constant. So this is how you have now successfully entered the condition y of 0 is equal to t1, and then you can press shift enter and you can get the value. You see now in this scenario we do not have any arbitrary constant because we have given the value boundary condition over here. So this is how you are going to take care of boundary conditions, initial value problems. So I think you have found that the syntax for the Dsolve function is pretty much easy and quickly to follow around. Let's move forward and take it further from here. So now we are going to give you an example of how to solving symbolic solutions to ODEs, which is ordinary differential equation. So once you know the syntax, this is the journal solution for an ODE. So this is y dash x is equal to function of y of x is the function and the variable x. And you see it gives me the value. As it gives, Dsolve gives rules, you can get the list of rule over here. And you see a journal solution contains arbitrary parameters, C1 in this case, that can be varied to produce particular solutions for the equation. So when an adequate number of initial condition is specified, Dsolve will return a particular solution. So here, if I give the initial condition of y at 0 is equal to 1, and then I enter it into the same function by giving the curly braces, you can see returns a particular solution for this problem at this initial condition. And then we can have maybe have a plot of this. So maybe we can do a plot and you say, okay, y of x, and you replace it with the solution 1, which is this solution, and then you can give some range of you need to do -3 to 2, and you can also see the plot of your solution. So you solve the differential equation, and then you can also solve it for any particular solution and can see the plot value of that as well. Let's move forward. Let's do some how you are going to if you have to solve the symbolic solution of ODE as a pure function, how you do that. So before you saw that when we were using the function Dsolve, we specified as y of x. But in this scenario, instead of y of x, if we give the parameter y, the solution will be returned as a pure function. So what is the advantage of getting this is because it will be useful for verifying the solution of the ODE and for using it further analysis. So we can see it in an example. So we have an equation with some initial value condition, and we can get, now you see we get the result as a pure function. And then we can, once we have this as a pure function, we can get the equation and then see it if it is for this is true. And we can verify the result of our things. So both are true in this scenario. Let's take another example. This is the example of a linear pendulum equation. So this is the equation of a linear pendulum. So this is a second order differential, y double dash x with yx is equal to 0 with some initial value condition of y of 0 and y dash of 0. And you see, instead of giving y of x in this parameter, we give y. The advantage of that, we get the result as a function now. And now we can draw this function for certain values of x for this solution, and we can see the plot value as well. So this is the advantage of solving it for y instead of y of x if you want to have the results in the form of functions, which you can use further. Let's take some more advanced examples. So this is an example of solving a logistic Riccati equation. So this is the Riccati equation over here. So this is the equation. Y dash of x is equal to y of x with 1 minus y. So this is the logistic Riccati equation with some initial value. I gave it a, solve it as a pure function, and get the pure function value. Once you get this pure function value, you can plot the solution for different values of initial values. So you see here, rather than giving a specific value, we gave a. So now we can give different values of a. So what if the y of 0 is 1 over 13, when y of this is half, or when this a is equal to 4. So in these three different scenarios, we can have a particular solution for this logistic Riccati equation, and then we can have the plot over here. You can notice how Mathematica or Wolfram Language has automatically given different colors, so you can tell that apart. You can also add a tooltip over here, which I have showed you how to do that in using the plot function. And when you hover around, it will tell you which function is which. Let's take another example before we move forward. This is an example of solving a Bernoulli equation. So this is the standard form of a Bernoulli equation, which is a first order equation of this form, where y of x plus some constant p x, y of x, some constant q x, y raised to power x. So this is the equation I can use for Bernoulli solving. So you can enter the equation, and then you can solve it by Dsolve. So you see the syntax remain the same. Dsolve equation, we solving it for y and x. Now we are solving it for y, so you should have up till now understood you should be getting a result in the form of a pure function. And then you can replace it by the solution equation and replace it by this solution to see if your result is correct or wrong. So you see both the functions give, and you can verify your result from here. So this is an example of showing the Bernoulli equation. Okay, so let's move forward, and now we will talk more about partial differential equations, or PDEs, which occur naturally in applications, and they normally model the rate of change of a physical quantity with respect to both space variables and time variables. So the order of the PDE is the order of the highest derivative that occurs in it. So let's take an example. So here is an equation, a PDE, partial differential equation over here. And you can see in Mathematica, we can directly enter it as escape, PD escape, and Wolfram Language understand that what it stands for, partial differential equation. So you can directly enter your equation in this format, and then you can see the solution by replacing the same Dsolve function. So because this is partial differential equation, so we have more variables, x and y, space and time, and we see for the first solution. And you get it. And then similarly, we can replace with the solution to see if it is true or not. So this is one way of how you can enter this equation. Another way, which is you want to do, is you can write in the proper Wolfram language system. So maybe I say it, so this will be going into, this will be translated as d derivative of u, which is again a function of x and y. So x and y, and it is with respect to x, so comma x. So this whole has been translated into this. Then plus x by itself, because this, and then for this, similarly in this method, we'll have like d of u, and u again is a x and y. So this goes by x and y, and this is for with respect to y. So we have y here, and this goes like this, and then is equal to sine of x. So we know is equal is double is equal sine of x. So this is the same way you can write it in this format as well. But Wolfram language also understand this format because it understands this function. And if you do not know the shortcut, you can always use the math assistant palette or the classroom assistant palette to type this. And we can save this as equation test maybe. And then similarly, we can do the solution for that. So this will be solution of test, and we can do it by Dsolve. So the first part is the equation. So this is the whole equation. So this goes here. Okay. And then the other parameters is the main u and the variables x and y. And you can then solve it by pressing Shift Enter. And you see the same result as here. And then you can also test it, equation test, by replacing it with the solution test, and I want to test it for first value, so I can park the first value. Always good to use a simplify, so you can simplify it to the last level. Equation, okay, so this is S. So this is true. So you can also solve in this matter and you can verify the result. Let's take another example, which is of the transport equation. So this is the transport equation, which is a linear first order partial differential equation. You can find the general solution with Dsolve. So I save this as a transport equation, use Dsolve, equation u, x and t, because here x and t are two variables. We solve it for that, we get the answer in form of a function. To get a particular solution of the transport equation, you can give an initial value. So I can give the initial value, ux of 0 is equal to e raised to power minus x squared in this scenario, and you can solve it with the initial value. And now you see there is no arbitrary constants available over here. And then finally, you can use the manipulate function, change the values, and if you run it, you can see a wave traveling towards the right. So you can see how you can solve the equation and then verify it and then even have some animation out of that. Let's take another example, which is a linear homogeneous first order PDEs with constant coefficients. So the equation is linear because the polynomials here p, q, and z are linear, and there is no term free of z, p, and q. So this PDE is also homogeneous. So I define this, and then we can solve it for general solution by using Dsolve. We get the general solution, and there is an arbitrary C1 of the argument 2y minus 3x. We can verify the solution, similarly replacing the solution, and we can see this. And then we can find a particular solution for this homogeneous partial differential equation by specifying some value of the constant. So in this way, I say make it a function of sine of a, and we can do a particular solution for this. So once you have a particular solution, you also may be interested to have a plot. So maybe have a plot 3D of this particular solution, and because it is 3D, so we have to give both x and y domains. So we say that x will go from maybe -2 to 2, and y domain will go from -7 to 7, and I can have a 3D plot. And you know, in Wolfram language, all the 3D plots are draggable. You can zoom in, zoom out, look at different features from different angles for that. So see, in a very short step, you can solve the equations and then have the 3D plots over here, all quickly. Let's move forward and take an example of a second order partial derivative equation. So this is the journal form of our partial differential equation, where u is a function of x and y variables, and a, b, c, d, e, f, g, and functions of x and y only. They do not depend upon u, so they are independent. So let's take an example of journal solution for Laplace equation. So this is the Laplace equation with some. So we define the equation, and then we can use the Dsolve on this equation to solve for PDE values. And you see that the journal solution here contains two arbitrary functions, C1 and C2. So the arguments of these functions, like y plus I of x and y minus I of x, indicate that the solution is constant along the imaginary straight line. So when y will be equal to minus ix plus alpha, when c1 is equal to 0. So these straight lines are called characteristic curves of the PDE. So in general, elliptic PDEs have imaginary characteristics curves. Let's take some examples on initial value problems. So Dsolve can be used for finding the general solution to a differential equation. And then you can use some initial value conditions to find the particular solution to know about the condition related to the area of application. So as this is the linear equation, y of dy of dt with respect of t. We define the linear equation. So this is a linear first order ODE, ordinary differential equation. And then we can have the general solution with the arbitrary constant values, C1 in this scenario. Now let's solve the same problem with general initial condition of y of 0 is equal to 4. So when we give y of 0 is equal to 4, we can get the particular solution for this ODE. We can verify the solution by replacing it with the particular solution, or by replacing with the initial condition of 4 on this, and see if the result was correct. And yes, it says that the initial condition for this particular solution should be 4. We can now also solve the same problem with the general condition of A. So rather than giving some specific value, we can define a variable and say solve it for A. And the advantage of having this A is that when you want to plot several curves of the equation for different values of A, you can see the inflection point of the solution and where it lies. So then you can have a plot of this particular solution with different values of A, in this case ranging from -2 to 2. And you can see the integral curves of the equation for different values of this A. The plot also shows that the solutions have an inflection point if the parameter A lies between -1 and 1, while a global maximum or minimum arises for other values of A. So this is very evident from the looking at this graph as well. Let's take another example of initial value problems with piecewise coefficients. So you know that the differential equations that arise in modern applications often have discontinuous coefficients. So, and Dsolve can handle a wide variety of such ODEs with piecewise coefficients. So let's take a solution with the general solution for a first order ODE that contains a unit step. So we can say Dsolve y dash of x, and we say let it be a unit step of x, and then we want to solve it for y and x. So because we use y, we get a pure function over here. So let's take the solution to the same ADI with some initial condition. So we can say that, for example, if we have an initial condition, we say that let the equation be same. So this is my equation. And once I have the equation, I can say give the initial value of maybe 1 to this, and we can save this as an equation, and then we can find the solution for this by using Dsolve, and then we can have like equation as the first, y, and with respect to x. So we'll have the solution for this at a initial value condition, and then we can then have maybe a plot of this. So we can have a plot of y of x, and we replace it with the solution, and we need to give the range. Normally I'm using -3 and 2, or maybe 3 in this case. Let's see. So the solution can be plotted in the Unius way, and you can notice from that the solution is continuous but not differentiable at when x is equal to 0. So is there a way we can verify that as well? So let's verify that, and we can verify it by doing like equation. We solve it for the equation, for the solution, for the first solution, and we want to see it for the x is equal to 0. So we say that x is greater than 0, and alternatively x is less than 0, and then we can maybe we need to simplify this and see if it is working or not. Okay, so after simplifying, we see that this is also verified that this solution is continuous, but it is not differentiable when x is equal to 0 in this scenario. So we can also verify it by this way. So let's summarize what we have up till now, the steps involved while working with Dsolve. So the first step we do is we set up the problem in using Dsolve, and then we get an expression for the solution. We can also verify by using symbolic or numeric techniques, or we can plot it. So that will be a visualization of the function, and we can use like a plot or plot 3D or contour plot depending on how you want to visualize that. So plots often reveal information about the solution, as you have seen in the previous examples. which might not be evident from the closed form expression. And if no boundary conditions are specified for a problem, the output from Dsolve is some form of a journal solution containing arbitrary parameters like C1 or C2. So you need to get a journal solution by that. So if there is no condition. So when you are using Dsolve, you also make any assumptions or encounters difficulty during the calculation. So it issues a warning outlining to the problem, but these messages can be ignored because sometimes they point to serious limitations in the answer given for that specific problem. So let's see at the summarize the syntax for the differential equation as well. So we looked at that. It has three major parts. First is the equation, second is the dependent variable, and then the independent variable over here. So how you write dy by dx is always y dash x, maybe this time 5 y of x is equal to 1, and y of x and with respect to x. So this is, we did it, and we used y of x, and you saw that the output for Dsolve is a list of solution for the differential equation, and there is a coefficient C1 because there is no initial condition was specified. The solution, but if you want to use this solution further work, I said that instead of y of x, we have to use y. So let's take this and I'll show you what the differences will be. So solution 1 is so now I get a pure function. Now the advantage of this, I told you, is that we can use it for multiple calculations, and let's see how we can use that for that. So here in this function it comes. So maybe I want to take apart from this solution the first part, and then if I use this as like a y of x, and then I can use it for y dash of x, or I can use the initial value conditions for that using those things. So maybe replace it, but so I can get the y of x from here. If I have to get y dash of x, I can get it directly by replacing it with m. So I get y of x, I get y dash of x, or even if I want to have some like initial condition, I can use that, replace it with the solution. So this will make the work easy for me if I have to use this function in further analysis or further work, rather than just giving the y of x and getting the results like this. And then we notice that we can always like verify the solution. So you can also use, after even by solving y of x plus 5y, let's retype the equation, and then we can replace it with the solution 1. If we simplify this, it will verify this, and then I can also have the plot for this. So we can use the plot function. So because we have to solve, so we will also need to use the evaluate function over here, so that it will evaluate this first all equation which I'm going to do, and then we'll use the plot function which is nested on top of that. So now y of x, and I give this the solution 1, and maybe I'll copy this C1 raised to 1 and x raised to -7 to 7, and the plot range all, and we can see the visualization for that as well. So in this way, you can have uh, this is a quick summary of how you set up your problem, how you solve your problem, and then you get the visualization or use that function into further analysis as well. What happened? That is, I think, all for today. And somehow my screen has also gone black. So if you have any questions, you can type in the questions. That will be all for today. So this is the basic introduction of using differential equations in Wolfram language. And we were using mostly the symbolic way. So the next session, most probably I'll focus on the ND-solve function, which will be numerical solving of the differential equations. So with that, I thank you everyone and thank you for joining me today. Have a good day. Thank you. Bye-bye.